Hey class, we are in the very last lap of Unit C, taking a look at measures of centrality and dispersion, and we're looking at something called the coefficient of variation. Now, in the last couple of units here, we were taking a look at the standard deviation, and the standard deviation is the best single measure that we have for dispersion, but it's not without its faults. One of the problems is that it's affected by extreme values, just as the mean is, right? In fact, it uses the mean in its calculation. So when we were talking about what's the average income of people in our class, then if Bill Gates is here in our class and we've got an average income of $43 million, and that's not a very good representation of how we actually, what the actual average income is. Same with standard deviation, because the mean is used in its calculation. So it's affected by extreme values. Another problem that we have is that you can't just take a look at the magnitude of the number and compare one standard deviation to another unless they're in comparable units. And so let me give you an example here. Suppose I've got two populations and the standard deviation of x is 12 and the standard deviation of y is 4,000. Which one is more spread out? Well, you'd look at this and say y is more spread out, but it really depends on the magnitude of the numbers that you're dealing with. So, for instance, suppose that x represents ages of kids in a family. 12 would be a huge standard deviation. Remember that a standard deviation is similar to, say, an average deviation, where an average of absolute values, where it's the average amount that a value differs from the mean. So if we were talking about a standard deviation of 12 as ages of kids in a family, that's saying that every kid differs from the mean by about 12 years. That's a huge spread. And you're not going to find standard deviations that big unless you got two kids and they're born a lot of years apart. 4,000 could be actually very small if we're talking about, say, house prices in Red Deer. Now, the average house price in Red Deer is somewhere between $300,000 and $400,000. We're going to use 300,000 in the example, in the calculations that we're going to use here. I think it's closer now to $400,000. But when we're talking about 300,000, remember, if we're using the empirical rules, that means that about 2/3 of the houses would be within one standard deviation of the mean. So about 2/3 of the houses would be between 296,000 and 304,000, and we know that's not true. That's goofy. I mean, the standard deviation is way bigger than that. Okay, it might be $25,000 or even $30,000, that sort of thing, right? So when you're talking magnitude of hundreds of thousands of dollars there, 4,000 is actually very small. So it really depends on the scale of the numbers that you're dealing with here. Fortunately, two standard deviations can be compared if we eliminate their units first. And so that's going to give us a measure of relative spread. I want you to remember that term. Measure of relative spread is a coefficient of variation. And it's measured like so. You take the standard deviation, and you divide by the mean, and you multiply by 100. If you don't multiply by 100, it doesn't matter. It'll just be expressed as a decimal value. And you can think of that as being the standard deviation as a percentage of the mean. Or if you're dealing with it as samples here, would be S divided by X bar. And again, whether you multiply it by 100 or not doesn't really matter here. By the way, we would not be comparing X and Y in this particular case. We would not be comparing family, ages of family spread versus the spread of house prices. But what we might be doing is comparing the spread of house prices back in the 60s to what it is today. So when you're dealing with changes over time, it's actually very, very useful. Or if we're, say, comparing comparable kind of things, like we're talking about the spread of house prices in Edmonton versus Red Deer versus Calgary, we come up with a coefficient of variation for each one there, even though the means might be different. So let's take a look at what we've got here. Suppose this is class exercise number 49 on page C28. Suppose variable x in the above example has a mean of 15, and variable y has a mean of 300,000. Which variable now has the greater relative spread? So let's take a look at family x here. And remember, what we're using here then is these standard deviations up here. So 12 and 4,000. So the coefficient of variation then of family x then would be the standard deviation divided by the mean times 100. So in this case would be 12 divided by 15 times 100, and that comes to 80, like so. Okay, and then the coefficient of variation of the house prices, so this would be y, would be the same formula here. This would be 4,000 over 300,000 times 100, and that comes to 1.33. You can see that the spread is much higher here than it is here. So in terms of relative spread, x has a much higher relative spread than y. And again, think in terms of ages of kids in a family. That's a big spread when you're talking a standard deviation of 12. But when you're talking about house prices of $4,000, that's a really, really small spread. So the relative spreads then are smaller. Let me drive this home with an example here. These are 5 children that have ages in the family here. Let's calculate the coefficient of variation. And what I'd suggest that you do here is that you stop the video at this point and you actually calculate the mean and the standard deviation, and then calculate the coefficient of variation, which is a measure of relative spread. So I'm going to assume that you have done that. Remember, don't just passively follow along here. Actually, when I say to stop and do it, please do that, because that's the best way that you will learn here. Let's go and calculate out for each one. I'm going to go to a more interesting color. Mu is equal to the sum of the x's over n. And so if we were to add these up, we get 2 plus 4 plus 7 and 10 and 12. Divide that by 5. And what we would end up with then is, what do we get here? $35 over 5 is equal to 7. So we get a mean of 7 here. The standard deviation here is, I'm just going to jump right to the square root here. The computational formula that we'll use is this. This would be the square root of, and we'll take each number here and square it. 2 squared plus 4 squared plus 7 squared plus 10 squared plus 12 squared. Divide that by 5 minus 7 squared. And then take the square root of that, and we will end up with 13.6. So I've jumped over the variance and taken the square root and just come up with the answer, which is 13.6. right there. Hey, one thing I want you to remember about calculating standard deviations, a really common mistake that people make is they'll add up the values and then square them. That is not the same as squaring each number and then summing them up. This is actually incorrect here. So it would be incorrect to add up the numbers and get 35 and square that and then divide by 5 and then multiply off 7 squared. That is not the sum of the x squared values. You have to square each number as you go along. In other words, it's not the square of the sum, it's the sum of the squared. Okay, anyways, the coefficient of variation is going to be equal to sigma over mu times 100, which is going to be 13.6 over 7 times 100 is equal to, oh, I need to back up here. Sorry, folks. This actually is the variance. The standard deviation comes to 3.69. So the variance is 13.6, and then we take the square root is 3.69. So I just need to change this a little bit here. All right, so we got 3.69 divided by 7 times 100, and that comes to 52.71. All right, now, what will their coefficient of age variation be 40 years from now? And so again, stop and calculate this and see what you get. And the question is, are the children relatively closer in age to each other than they are when they're young or when they are older? So I'm going to calculate the mean to be, well, all we've done here is we've added 40 to each number. So all I'm doing is adding 40 to each number here. So the mean will not be 7, but it'll be 47 if we've added 40 to each number. And you can go and calculate that out. The variance turns out to be exactly the same. This is the way that I actually demonstrate this if I was standing in front of you in class, and so I'm going to have to describe it. You'll just have to picture it in your mind. But what I do is I hold out my hand, and I, with the fingers splayed, and so you can see the fingers 1, 2, 3, 4, 5, and they're held out in front of me. And I'm standing at a certain point on the floor, and so that represents when the kids are young. And then what I do is I walk towards the left. So this is, well, my left, your right. And so the numbers are getting larger and larger and larger. So in other words, we're going to add 40 to each one. So instead of the original numbers being 2, 4, 7, 10, 12, they're now 42, 44, 47, 50, and 52. Now, as I move my hand along that number line, does the spread of the fingers, or in this case, the spread of the numbers, change? And the answer is no. So the actual standard deviation doesn't change. And picture that in your mind, that the numbers, the fingers are not getting any more spread apart. I'm just simply moving the whole bunch of them 40 over. So I've added 40 to each one. By the way, that's why we say that the standard deviation is actually independent of the mean. That sounds kind of a goofy thing to say, because isn't the mean used in its calculation? And the answer is yes, but once you subtract the mean off of it, all you're left with is deviations. And those deviations then are the same, in this case, whether they're at very low ages or whether they're at very high ages. So the standard deviation is the same, and you can go and calculate the numbers and you would find that out. The mean is just 40 years more, so it's 47. So the coefficient of variation is going to be sigma over mu times 100. The numerator doesn't change. The denominator now is 47 instead of 7. And so what we end up with then is something which is 7.85. So what we have here then is that the coefficient of variation when the kids was younger is much higher than it is when they're older. And practically, you know what that means. I mean, if you take a look at kids in a family, you'll see that there's a big difference between a 2-year-old and a 12-year-old. Those ages are quite spread apart. But when they're adults, there's not much of a difference between a 42-year-old and a 52-year-old, is there? I mean, they're probably in the same stage of life, even. And so we would say that the relative difference in the ages is less. By the way, just as kind of an aside here, which I found kind of interesting, is that, you know how they say that when you get older, time actually speeds up? Well, in a sense it does, because what we're thinking of actually is relative time. We're thinking of the coefficient of variation. Think of it this way, is if you're a 5-year-old kid and you have the most awesome summer ever, and that summer seems to go on and on and on because you're outside playing all the time and all that kind of stuff, you've actually used up, in that particular case then, there's 12 months in a year, 5 times 12 is 60, so you've used 2/60ths of your life, so that's 1/30th of your life in this awesome summer. Now, instead of talking about a 5-year-old, talk about a 50-year-old, and instead of talking about 1/30th of your life, you're talking about 1/300th of your life. So you see, that's a relatively smaller time period in terms of your whole life, and that's why it seems that time is actually speeding up, where of course we know that absolute time does not speed up, but relative time does, because we accumulate it as we go. So a summer is only 1/300th of your life when you're 50th. So that's an interesting thing here. Let's just finish this off here and say, now let's age these kids by 300,000 years. And if that sounds kind of goofy, think of it then in terms of house prices. So if we take a look at the original numbers there, which were 2, 4, 7, 10, 12 at the very top of the page here, and we're going to add 300,000 to them. We've got 300,002, 300,004, 300,007, 300,010, and 300,012. What's the mean? Well, it was 7. Now it's 300,007, because all we've done is add 300,000 to each one. What's the standard deviation? 3.69. All we've done is we've taken these kids and we've aged them 300,000 years. The absolute spread between them hasn't changed at all. So the standard deviation is still 3.69. But the coefficient of variation now is going to be sigma over mu times 100, which is going to be 3.69. Numerator is the same. Denominator is 300,000 and 7. And that's something really, really small. It's about 0.0013. And that's after being multiplied by 100. So it's really, really small. Think of these, maybe not in terms of ages of kids, but in terms of house prices. And if you had 3 houses that you were trying to decide between, and the house prices were 300,002 all the way up to 300,012, you would consider that to be negligible. That would not even enter into it in terms, and of course nobody would actually price a house like that. But there's virtually no difference then between them. $10, right? and that would not enter into your decision at all. So the relative spread is minute here, although the absolute spread in terms of standard deviation is still 3.69. So that is very useful when you're talking about changes over time, or change, or one city to another city where they have different means. So that actually ends this particular unit here. Please remember that there are additional problems at the end here. And so they start on page C29, and you'll be calculating measures of centrality and dispersion for both grouped and ungrouped data. And then you'll also be calculating some coefficients of variation and empirical rules, and you'll have answers here. Make sure that you have worked through these problems